So let us now introduce fractional ideals. So let R be a commutative domain and say K is its fields of fraction. So fractional ideal of R is an R module I which is contained within the field of fractions K, such that for a non-zero A in R, this AI lies within R. So basically this A is just clearing the fractions. So let us make some remarks here. So first remark is, informally you can think of fractional ideal as a non-zero R submodule of K, because it is contained within K. So we're writing it as I, it is contained within K, and elements of which have a common denominator. So when you multiply this by the common denominator A, it ends up lying back in the ring R. So important point number 2 here is, this is very important, a fractional ideal is not an ideal if you are considering in the entire field of fractions K, but if it is contained within R, then it is an ideal. So if I is a subset of R, it is a fractional ideal if and only if I is an ideal in the underlying ring R. So this is important. So every time we take the fractional ideal and we are considering it in this underlying ring R, and this I is a subset of R, then I automatically becomes an ideal of R, and we will use this fact implicitly. But we have to keep in mind that if it lies outside R, then it is not an ideal. So let us do an example which makes this point more clear. So say this ideal generated by 1 by 5 in integers. So this lies within rationals. So what are the elements of this ideal? So they consist of A, where A is an integer, so this lies in it, because element 5 would lie in integers, and 5 times 1 by 5 will give you 1, and that would give you the entire set of integers. So if you go back to the underlying ring, you will get this integers, but you will also get fractions of this form b over 5, where b is an integer. So it just consists of two such sets. One is just integers, and second is fractions of the form b over 5. Notice that 1 is part of integers here, and that's precisely why we are saying it is not an ideal, because this is not the entire set rationals. So if it was an ideal in this rationals, then it would be entire set of rationals. It is not the entire set of rationals. It is just all integers and fractions which would have denominator as 5. So obviously if you multiply throughout by 5, so this, if you set this A as 5, you get back to our ring Z. So our ring here is Z, and field of fractions is just rationals. So this is a fractional ideal of Q, or rationals. But if you consider localization, then this is not a fractional ideal, because localization you have forms like S over T, where T is not divisible by 5, and then you do not have actually a number which will clear off all these denominators. So number 4 remark is that set of all fractional ideals of R form a commutative semigroup with the unit element R itself. And to see this, we have to define the product of fractional ideals, and then it will just pop out. So product of fractional ideals, say I1 and I2 are two fractional ideals. So then you can talk about summation AI BI as sum A1 BM B1 all the way to AM BM, and I goes from 1 to all the way to M. So this AI lies in this first fractional ideal, and this BI lies in the second fractional ideal. And you can immediately see that actually if you restrict it to the underlying ring R, if these fractional ideals actually lie in the ring R, then this is precisely how the product of two ideals is defined. So this is a non-zero R submodule of K. So it's contained within K, which we are calling as R submodule of K. So say there are two non-zero elements, X and Y in R. So X clears the denominator of I1, so X I1 lies in R, and Y clears the denominator of I2, so Y I2 lies in R. Then you can consider some element alpha of this I1 times I2. So this alpha lies in I1 times I2. And we are going to show that this will also be a fractional ideal, because now you can clear the denominators of alpha by multiplying with x and y, which we would expect. So you just sum it over xai and then ybi. So this clear the denominators of I1, because these ai's lie in I1 and x is clearing the denominators, and here y is clearing the denominators because y clears the denominator of I2 and these bi's lie in I2. So this lies within R. So this xy, so instead of a you can say this element xy is clearing the denominators. So now we come to principal fractional ideals. So for a non-zero a in the field of fractions, we can define a fractional ideal as this a, which is defined as AR. So this is generated by a single element. So a fractional ideal of this type is called principal. So if you are given so this a is in K, so you can also have product of two principal fractional ideals. You say a times b, you can define it as AB, which you can say is AB in R. Now again notice that B lies in K, so you can also say that AB lies within K. So that is it. So this AB is also now a non-zero element of K. So now we come to another important aspect of fractional ideals, and now we're going to talk about invertible fractional ideals. So you start I with a fractional ideal of R, and this R has field of fractions K. So now we define a new ideal J, which is x within K, such that xi lies within R. So notice that now this x is within K. For fractional ideal, we had this ai lies within R. This a is in R. Here x is in K. So the first thing to notice is that this J will still be a fractional ideal. So to show this, what we are going to do is we take these non-zero elements y and R. So y lies in fractional ideal I, R lies in R, so that their product lies within R. So this small r is clearing the fractions here. So then ry would lie within R intersection I, and for example in here, if you consider something like here, this y is say 2 over 5, and this R would be, you take 5, then their product is 2, which would lie within our ring R, which is integers. So this ry would lie within R intersection I, because this I is a fractional ideal. It contains all the integers and all such fractions, and 2 is an integer. So 2 lies within R intersection I. So this is you can see this clearly via an example. So this ry lies within R intersection I, and then for every a in J we have ary lies within R. So this makes this a fractional ideal. So J becomes a fractional ideal. Now this I times J lies within R. So if the equality holds, we say I, which is a fractional ideal, is invertible, and we denote J as I inverse. So the story is that if you have say 2 by 5 living here, so 2 by 5 is living in this ideal I, you want 5 by 2 here in this J, so that you can generate a 1, so that you can get this underlying ring R. So these two will cancel out, and therefore you have to pick up elements which lie in the field of fractions so that you can hold this condition. So the idea is precisely you want to generate ring R with two fractional ideals. So you denote this J as I inverse. So now our first proposition. So this is every principal fractional ideal is invertible, and set of all invertible fractional ideals form a group under multiplication. So let us see the proof of this. So let I be generated by this single element like this. So that is our definition of being a fractional ideal, which is principal. So now you set J as A inverse of R. This will give IJ as R. And you can always take inverse of this and get back here. So I inverse of, again, inverse is I. So now we will prove this kind of tautological statement. If these product of two fractional ideals is R, then both I1 and I2 are invertible, and you can say I1 inverse is I2 and I2 inverse is I1. So we are just going to show that I1 is invertible and I1 inverse is I2, and since this is a commutative ring, everything will follow for I2 also. So first thing is this I1 times I2 is equal to R would imply that I2 lies within I1 inverse, because I1 inverse would contain all such elements. If you multiply them, you will lie within R here. So R is equal to I1 I2 I1 inverse. This would lie within R from this relationship here, and that would essentially give you I1 inverse is R. So we have seen that I1 is invertible because you have this equality right here. So you have invertibility if you have this equality instead of just this relationship. So now this I1 is invertible. Now we show I1 inverse is I2. So I1 inverse, you can say I1 inverse in ring R. So this will be equal to I1 inverse I1 I2. But these two parts will now become R, and this R I2 is just I2. So it's very tautological. So now we come to the definition of a Dedekind domain. So Dedekind domain is a domain R which is not a field, and every fractional ideal is invertible. So again, Dedekind domain is a domain R which is not a field, and every fractional ideal is invertible. So in the next lecture we will show that how this definition is equivalent to the definition we have given before, that is Dedekind is Noetherian, normal, that is integrally closed, and of dimension 1, that is every prime ideal is maximal.